So last time we saw that omega spectra are really types of sequential spectra that we'd like to study with regards to the stable phenomenon. But of course, not every sequential spectrum is an omega spectrum. This proposition states that for any sequential spectrum X, we can construct a corresponding omega spectrum, QX, such that there is a stable weak homotopy equivalence between X and QX, which already justifies using it to study the stable phenomenon. Furthermore, this map actually becomes a strict or level weak equivalence precisely if X was already an omega spectrum. Furthermore, two sequential spectra are stable weak homotopy equivalent precisely if their corresponding omega spectra are level or strict weak equivalent. But now we need to actually construct QX, and after that we'll return to this proposition and prove it. This process is called spectrification because what we're going to do is take our sequential spectrum and continuously break it into other spectra. And once we have this massive collection of spectra, we're going to combine them. So we start with a sequential spectrum, and we're going to want to consider them equipped with their adjunct structure maps because an omega spectrum is concerned with that. Okay, so let's consider just one piece of this. We recall that since the original component spaces are compactly generated topological spaces, which has a model category structure on it, we can factor the original adjunct structure map as a projective morphism followed by an injective morphism, in particular as a generating cofibration or an isotope relative cell complex followed by an acyclic fibration, which is in particular a classical weak equivalence. This will be important in proving one of our earlier propositions. So this intermediary space is z1, k, and for notation we'll rewrite the original component spaces in this way. Well, as you can imagine, we want to make a new spectrum with component spaces these z1, k. If we apply the loop space functor to that top arrow, we can construct the bottom arrow to the loop space of z1, k. Then we define the new adjunct structure maps as the diagonal map followed by the bottom horizontal map. We can do this for all k, i.e. all original component spaces, to get a whole new spectrum with component spaces z1, k right next to this original one. But now we could just apply the same process to this new spectra, and so on and so forth. Ultimately, we end up with some huge collection of spectra, and just to see what we've done, I've drawn it like this, with the blue representing the original spectrum. Now, I think that's pretty cool. Okay, and now we want to package all of the relevant information from that into a single sequential spectrum. So it is what you might expect. The component spaces for this new spectrum, QX, are the colimits over I of the zi, k, i.e. over each row in the diagram from before, and the adjunct structure maps are also defined as a colimit. The only ambiguity is whether the colimit of the loop spaces of all these intermediary zi, k is the loop space of the colimit. But since each component space is compactly generated, stemming from our original definition of omega spectra, and since S1 is compact, we do have Cartesian closure, so the internal hom here does preserve colimits. So now to return and prove the proposition. One general observation that we will be using is the following. By our factorization, as in particular a relative cell complex on those top maps from before, followed by a weak homotopy equivalence, we see that the colimit is a transfinite composition of relative cell complexes. We then recall that the image of a compact set intersects a finite number of cells, and since in particular spheres are compact, the image of an element in any homotopy group is actually achieved completely at some finite stage. So for the first statement, we use this fact. The diagonal maps here in our factorization are weak classical equivalences. This is preserved when we pass to colimits. The only ambiguity is that our image of something in the homotopy group is actually achieved at a finite stage, which our previous remarks just cleared up. So it does appear at a finite stage. So a cycle on top is weakly equivalent to a cycle at the bottom, in particular when we pass to colimits, and thus the adjunct structure maps, which are the colimits of these dashed lines, are weak homotopy equivalences, and so QX is indeed an omega spectrum. Regarding the second statement, observe that this sort of backtracking maneuver in spectrification. We move along the diagonals, which are weak equivalences by construction, in order to get an element that is related to the original component space. So to see that we have stable weak equivalence, we observe that on the left we have the definition of the qth stable homotopic group of a general sequential pre-spectrum, and on the right we saw that this is how we characterize stable homotopic groups in omega spectrum. We want to show that this map is an isomorphism, and we just use the backtracking method. The idea is that the qth homotopic group of the k-fold loop space of k of xk is the q plus kth homotopic group of xk. For the third statement, let a to x again be the map from x to qx. First we'll prove the reverse direction. Well, if x is an omega spectrum, then these vertical maps are weak equivalences. Well, by the model structure on compactly generated topological spaces, we know that classical weak equivalences are closed under 2 out of 3, so the top map is a classical weak equivalence as well. So again, a cycle in X passes through a sequence of acyclic maps, those ones up top, and is actually achieved in a finite stage because spheres are compact, and so we have a weak equivalence. To see the other direction, consider the homomorphism between X and QX. Then the top map is a weak equivalence by assumption, and we already showed that the right one is, which also implies the bottom one is. Then by commutativity, the left one has to as well, which shows that X is an omega spectrum. The other statements follow analogously, so let's move to the final remark. So while we did all that work in finding resolutions to construct QX, it turns out that this is unnecessary in the case of CW complexes, or CW spectrum. The nLab contains references to this fact, which we don't prove here, but this is a very nice simplification.